And we ended up taking the tent down or taking the chairs down that day. It was still pouring rain. I ended up wearing a garbage bag because I was dressed up, right? You know, I was in a coat and tie. You take a garbage bag and you pull a hole in the top and put it down over the top, you know, and you tear a hole out for each arm, and at least keeps your shirt dry. It's very stylish too. You will find probably that it's a good idea to carry a garbage bag with you in this climate, in the bottom of your pack, so that when you get caught in a rainstorm, well, you need two things. You need a garbage bag and you need a big red bag from the campus store. The garbage bag you put over your body, and then you put the big red bag over your head and hook the handles over your ears to hold it on. It really is stylish. Haven't you ever done that? Yeah. I have. That's Ithaca. Saw this really cool article over the weekend. It was this group has built an analog circuitry. It's on silicon, but they lifted the silicon off and put it on some sort of silicone rubber and put it between two layers of silicone so that they could adhere it to skin. It has the same modulus of expansion as skin, has the same stiffness as skin, and it's near enough in properties that it'll adhere to your skin by van der Waals forces. And so it is a no adhesive silicone patch that has arbitrary electronics on it. So you can do like EEG measurement. You slap the patch on somebody's upper arm or chest, and you get EEG, and no electrode paste problems. Very cool. I'm looking at my arm here. I realize I got red dots all over my arm. I was mowing poison ivy on Saturday. Probably a bad idea, but oh well. Any questions about the first lab? Any questions about the reading? I don't know. Nobody reads until the lab is due. But you really do need to do some reading of the Altera documents before lab. It's a 2-week lab, but you are graded on how ready you are to do the lab in the first lab. So that's this week, this Friday. First lab is this Friday. And we will be interested in what you know at that point. Let's see, I think I talked about what Lab 1 was, which is a one-dimensional cellular automaton on Friday. But I don't think I got much past there, right? That was the last thing? Yeah, okay. So we want to talk a little bit about the technology now for Lab 1, particularly static RAM, use of static RAM, and the VGA interface. And then we will do some Verilog code to, as an example, related to Lab 1. I'll do another automaton. I won't do the Lab 1 automaton. That would be boring to give you the answer. So I'll do another automaton, which is a 2-dimensional version. So there's at least three types of RAM you can use. I'm going to talk about 2 today. One is the so-called M4K blocks, and the other is external RAM. So M4K blocks, which are on the FPGA, There's 104, 105 of them on the FPGA. M4K blocks can be configured to be single port RAM. They can be used as register arrays, or they can be used as ROM, as read-only memory. And the way you use them from Verilog determines what they become. Now, there's actually two ways of using M4K blocks. One is to infer M4K from Verilog, and the other way is to tell the compiler using the Mega Wizard. You can use the Mega Wizard interface in Quartus 2. Look it up. Mega Wizard interface to directly specify M4K blocks. And then you're not, then Quartus 2 is not trying to guess what you want, but rather you tell the compiler what you want. I want a 16 by 16 or a 16 by 16 bit register bank with dual read and single write. And then that's what you get. You can also infer this, but you have to be careful about what you infer. So there's two ways of doing it. And some of the examples use inferred memory, and some of the examples use explicit memory through the Mega Wizard, so you can get some examples of both. The code example I'm going to give later today uses actually uses static RAM, so it's not inferring memory at all. But there are lots of examples which you should probably at least go through. See what's there on the VGA page, which is linked off the main page. There's a VGA page. The last example on the VGA page infers static RAM in M4K blocks and uses static RAM in M4K block for the state machine, for the cellular automaton. But let's say that you want to generate just read-write 16-bit RAM M4K. Have to erase the erased board here. The signal and noise is not very good. You can force Quartus 2 to infer RAM, read-write 16-bit RAM, using the following code template. This, by the way, comes from the HDL style manual. It's an Altera document, HDL style manual. It is highly recommended reading because it outlines how Verilog is interpreted by Quartus 2. Verilog is a general simulation language. Quartus 2 is Altera's implementation of Verilog, among other things. If you read this, it will give you some idea of how Verilog is going to be converted to hardware. Found it very useful. So let's make a module called RAM Infer. This will, as the name implies, clue, if you write a module in this format, it will clue Quartus 2 in to the fact that you want RAM. And we're going to have an output called Q, which is the usual sort of indication of a flip-flop output. Q, an address A, data input B, a write enable, and a clock. So this is an output. Well, we're going to specify that in a minute anyway. And so we're going to say output 15 down to 0 of Q. And for those of you that learned VHDL, this is the colon here is the same as the VHDL keyword down to. We're going to have input, which is 16 bits labeled 15 down to 0 of data. And we're going to make this a 256 word memory. So we're going to have an input, which is 7 down to 0 of address input, and input of 1-bit input of write enable and clock. We're going to define a couple of more internal registers of 7 down to 0 of read address, and I'll tell you why we're doing that in a minute. And then the main memory is going to be excuse me, a register of 15 down to 0 of mem with an array variable 255 down to 0. So this is 256 copies of 16 bits. And then to implement the memory, we're going to say always at pause edge of, sorry, that's not hyphenated, pause edge of clock Now, the fact that we're saying pause edge of clock here immediately tells you that this memory is synchronous memory. Right? It is clocked memory. There is no way, there's no way to make an M4K block asynchronous unclocked. It always has input latches and optionally has an output latch, but it is always clocked. So we're going to say that write enable high means that we want to write to memory. So if write enable, then mem of address A gets the value of D. There is two forms of assignment, blocking and non-blocking assignment. When you use the arrow equals, that's a non-blocking assignment. We'll talk more about the difference between that as time goes on. And then read address, non-blocking gets A. So on the clock, we're going to copy the input to read address and then end the always block, and then asynchronously assign Q to be the value of mem from read address. And then we're going to end module. So this is going to be a read through write. As soon as you write a memory address, its output is available rather than being delayed a cycle. The general rule is that in clocked statements, you are going to want to always use non-blocking assigns, and in unclocked statements in combinatorial logic, which can change at any time, you're going to want to use blocking assignments. Again, we'll talk more about that. Any questions about this? If you were to just mix these statements in your inline code, Quartus 2 may or may not figure out that you want an M4K block. If it doesn't figure that out, it will use logic elements to build memory, and you'll use up 256 times 16 logic elements, 16 bits of logic elements, which you don't want to do. So you need to isolate these statements into a module to force Quartus 2 to notice that they're M4K blocks. Again, any questions?
Why do they have a separate read address from A?
It's so that you can latch the value at the same instant that you're writing. So if A changes because the calling process, the calling module is changing A, it will be latched locally so that you read back the same value that you've just written. Now, we can also infer other kinds of memory. For instance, we can infer let's see, if you're used to MIPS kind of architecture, and a lot of people are because that's often an example that's used, you'll know that MIPS architecture requires that you do 2 reads and a write on every cycle to maintain a per cycle instruction rate. You have to read 2 registers, put them through the ALU, and then write back to memory or to the register bank. You can infer a register array by a module that, unbeknownst to you, actually uses 2 M4K blocks so that you can do 2 separate reads at the same time. Now, you don't necessarily know that that's what you're doing, but you are using 2 M4K blocks. So we're going to ask to have 2 outputs, Q and Q2, a write address a read address and a read address 2, and of course we need an input, input data, since we're only going to write one at a time, and a write enable and a clock. So in this case, we're going to have an output of 15 down to 0 of Q and Q2, an input of 15 down to 0 of D. It's only a 16 by 16 array of registers. So we only need 4 bits of address. So we're going to have an input of 3 down to 0 of write address, read address, and read address 2. And of course an input of write enable and clock. Then internally we need a register for the write-through addresses. For 2 addresses, and the main memory, which is a register of, it's an array of 16-bit values that are indexed by a 4-bit value. Yes. I'm defining those there. Those are not inputs. Those are defined internally in the module. Yes. I'm sorry. Yes, it should be 15 down to 0 because this is an index. You're quite right. Thank you. And then and again, since we are working with synchronous memory, we need to always clock the system. If write enable memory of write address is set to D, A1 gets read address, A2 gets read address 2, we end the block. We assign Q to mem of A1 and assign Q2 to mem of A2. and end a module. So nowhere in here do I say, use 2 M4K blocks. It just figures that out because you've asked for a dual read system. The only way to do a dual read, an M4K block can do 1 read, 1 write, or 1 read and 1 write per block. Some of the CPUs I've written in the past, I use this scheme for making a register bank. The last one I wrote, which is the one you're going to be using this semester, doesn't bother with registers because it's a stack machine. Now, quite often, you're going to want to build a table. Let's say if you're doing direct digital synthesis of sine waves, then you need a table of sine wave values that you're going to index through. You might find that you need a table of that's represents, say, the log approximate log base 2 of a number, and Quartus recognizes that if you build a module that is clocked and that has all constant values for the values of the case statements, for the targets of the case statements, that could be inferred as ROM. And we'll build a ROM using M4K blocks. Do you want me to write that out, or is that clear what I mean?
Write it out.
Write it out, okay. So we can write a module sync ROM. Data out. Input a clock. And let's make this a, what are we going to do here? Oh, well, we say one nice small little ROM that has the weirdest output is a ROM that takes in a hexadecimal number and puts out the pattern of segments for a 7-segment display, which is a 16 by 7 ROM. But I'll just use the one that's in the HDL manual here, which is a 8 by 6 ROM, 8-bit by 6. So we're going to input an 8-bit address and we're going to output a 6-bit value, and always at we're going to implement a case statement 8 bits of binary 0 is going to be the case we write first, and the Q value for that is going to be 6 binary bits and then we write the value for 8 binary 1. Q equals 6 binary bits. And we keep doing that until we get down to 8 binary, let's do it, H hex FF. The value for Q is going to be 6 binary bits of something. And then we do an end case. And an end always. And an end module. The fact that all of these values are constants means that we can implement this as a ROM. This has to be a complete case statement. There can be no case that is left unspecified. If you do leave a case unspecified, you get a latch. So you have to specify every case. This can get tedious for big arrays. And so I don't know how you handle text. What I do is I write a MATLAB program that generates Verilog for building big tables. I think some people here would probably use Perl. But I don't know Perl. I do know MATLAB. And Perl string handling is better than MATLAB, but MATLAB is better than C. So it all works out. Like, yeah, it's smart enough to know that the high order digits are all 0 if you don't specify. It's inferred. But oh yes, in C you can use X or H to represent hexadecimal. You can't do that in Verilog. If you put an X there, it gives you the strangest errors. Because X means I don't care. Don't do that. I've done that many times and always had trouble finding the error. Use H. In general, if you don't specify the number of bits in a number, Verilog defaults to a value you almost never want, all right, which is 32 bits. So you always specify the number of bits in a comparison or in a wire for both efficiency, because who wants to pass around 32-bit buses when you only need 6 bits, but also because comparisons can sometimes do very odd things, particularly if they're signed and you're comparing bit numbers from different width of buses. You will cut down immensely on your debug time if you specify a width of every single wire in every design you build. Takes a little more typing the first time, but as we all know, the time to get something running is dominated by debug time. And it's usually worse than that. It's usually the one error that takes 6 hours to find, and then all the others combined take only 6 hours. We've all had that happen. Any questions about this?
I was just wondering how the software will know that you're using the N4 bit. How do you declare the memory of 16 bits and
It analyzes the structure of what you asked for and says, will this work for an M4K block? If it will, I'll build it. As long as it is isolated in a module and is clearly recognizable to the system as probably being memory. Now, if you ask to clear all the values at t equals 0, it won't infer memory because M4K blocks can't do that. If you ask to clear memory in a single operation, you won't get M4K blocks, you'll get logic elements. So it has to be something that M4K blocks can do. You can find out what M4K blocks can do by Googling up Altera M4K block User's Manual, and you'll get more information than you could possibly want on M4K blocks. In fact, in general, if you want to find out about something on the FPGA, you Google up Altera User Manual X, where X is the name of the thing you want to find out about, and you'll get a very nicely written manual. First time I taught this course, I printed them all out because I like to read sitting on my couch. This was a while ago. I didn't have a laptop that was any good. It was a pile about that high. I don't expect you to read 2,000 pages. I told the first class I taught, I said, I read about 2,000 pages to get this class going. I think you will too. And half the people left. Not me. So it went from 30 to about 15 people in one lecture. And I figured, that's probably a little harsh. You don't have to read it all at once. You probably don't have to read all 2,000 pages. But there are going to be some things you really do want to read. One is the HDL User's Manual, which is only 30 or 40 pages, and well worth your time. And then if you want to find out more about if you want to do something really odd with an M4K block, do I have to register the inputs? Do I have to register the outputs? How do I get around registering the outputs? How do I do a quad read? If you want to do something odd, then you're going to have to read the manual. Any other questions? Darby.
You're saying that if you added reset logic inside that module, it wouldn't infer M4K block?
That's correct. If you added reset in there, so when reset was high, all of the memory was zeroed.
If you iterated through all the registers?
It won't do that automatically. If you iterated through all the registers, I don't know what it would infer. But certainly if you just say, if you zero memory in reset time, it'll implement it as random logic. Because M4K blocks don't have that function. They don't have a clear line. What do you mean by directive?
I know it's not very common to specify certain things.
There are a series of directives that you can use to refine what you want to do, and the list is very long. Now, one directive I've used fairly often is that you can put a directive on the line where you specify the memory. I just erase it. Where you say mem blots. On that very line, before the semicolon, you can put a comment directive which says load memory with the contents of this file. And then when you compile the design, part of the compiled design will be the contents of that file off of your hard drive put into the M4K blocks on the FPGA. That's extremely useful. There's a whole bunch of synthesis directives. You could Google up M4K block synthesis directive to find those out. But the storage one is just phenomenally useful. So let's say that you've built a processor and you've defined its memory to be in M4K blocks, and you want to then write a compiler on your PC that compiles to a memory image file, a MIF file, memory image file. MIF is a Altera extension with a very specific content for M4K blocks. If you compile to an MIF file, memory image file, then you can specify that that memory image file be loaded at compile time. And in fact, if you've already compiled the processor and its memory, there's a special way of bypassing the compilation process and loading a new image onto the processor, which means you can do a fast compile test cycle without recompiling the hardware. In other words, you compile the software, download it to the memory image file to an M4K block or 10, and then execute it directly out of the M4K block very quickly, 10 seconds. Quartus 2 is a huge system. It's evolved for at least 15 years, and they've never gotten rid of anything. So users will say, I'd really like to be able to do X. And they'll say, okay, we'll build it in for you. But nothing else goes. So it has a huge number of options. The only way I've been able to find them all is to kind of use Quartus as if it's a video game. You take a simple design, you get it to compile, and then you start looking through the menus for interesting stuff. It's an adventure game. You have to find the stuff, because there's no way you're going to read through all the manuals. Actually, the first year I taught this class, one of the people that sat in the first row was a IBM engineer who had used this very chip and very software for 6 years. And if it hadn't been for him, I never would have figured it out. But, for instance, in the Tools menu in Quartus 2, have you all downloaded Quartus 2 by now? Look in the Tools menu. In the Tools menu, there's a bunch of advisors. There's the speed advisor, the size advisor, the bunch of other stuff. And if you compile a design and then pull down the speed advisor, it'll say, if you tried X, Y, Z, this design would get faster. What would you like to do? This one costs you a factor of 2 in compile time. This one costs you a factor of 10. You click them all, and then you go have a cup of coffee while you compile, and you come back and it's 30% faster than it used to be. That's cool. Or it's too big. Well, I want to make it smaller. I want you to aggressively rearrange this system. It might take longer to compile. It might slow down, but it'll be smaller. Look at the advisors. Look at the tools. Look at the Mega Manager. The Mega Manager allows you to lay out memory blocks exactly the way you want, without Quartus being in the way. It's just you and the compiler. But now let's talk about one of the SRAM peripherals, unless there's more questions. SRAM peripherals. So the DE2 board has a 256K by 16-bit asynchronous CMOS RAM 15 nanosecond. What that means is that 15 nanoseconds after you give the memory an address, you will read back a valid value from it, independent of any clock. 15 nanoseconds after you lift the right enable line, or zero the right enable line. It's right enable is asserted low. 15 nanoseconds after you assert the right enable, you will have changed the value in whatever address is currently on the address lines. The default clock for the DE2 board is 50 megahertz. 50 megahertz, which is 20 nanoseconds. Oh, well, so this is fast enough to use at 50 megahertz. In fact, it's fast enough to use a little bit faster than that. The chip on the board has a bidirectional data line, 15 down to 0 in Verilog terminology. There is a right enable asserted low line. There's an address which is 18 bits, 17 down to 0. There is a chip enable asserted low. There is an output enable, which is asserted low. And there is a low byte, high byte, both of which can be asserted low. All of those lines are permanently connected to certain pins on the FPGA. If you set CE equal UB equal LB equal output enable equals 0, the way the chip happens to be connected to the FPGA is it has its own dedicated lines. Therefore, you don't need the chip enable because the only thing that's on the bits on the address and the data line is this chip. So you don't need chip enable. You don't need output enable for the same reason. You don't need lower byte and high byte enable unless you want to do byte addressing. Now, for some video applications, that's very handy. That's essentially an extra bit of address. but the way I'm going to be using it is as a 16-bit memory, and so I'm just going to lock both of those low. Enable both of them. If you do that, then you have a system which is controlled only by the address in the right enable line. If the right enable line is high, you get a read, and you get data here. If the address line, if the right enable is low, memory gets written by whatever address happens to be on the pins. Now, if you go through the data sheet for this SRAM fairly carefully, you will find that the setup time for the right enable relative to the address is 0. Which means that, let's say we're on a clock edge here, that right on that clock edge, we can change the address bus, and we can set right enable equal to 0 at the same moment, and the correct thing will happen. The correct thing being that sometime 15, let's say that this is 20 nanoseconds, 50 megahertz, sometime about here, the write will be done, and the data will be valid at that address. again, we can change A here and set the right enable equal to 1. And someplace about here, data will appear at the D output. The memory itself, though, does not care about clock edges. The memory is asynchronous. It is not clock. There's no clock input. Question?
No, I don't think there is our the word in
This?
I mean, the word
Right. Oh, yes, I left out a letter. I leave out lots of letters. I also, like I said, I invert letters. I flip P's and B's and D's and Q's. They're all kind of, I can't tell the difference between them necessarily. Yeah.
This is off by half a second.
Doesn't matter. It doesn't matter. The clock doesn't matter. This is an unclocked memory. You can change it anytime you want. You can change it in the middle of a cycle. 15 nanoseconds later, it'll be valid. This is a blessing and a curse. So, now the next step here is to talk about the example. What you're going to build for the first lab is a 1D automaton. What I'm going to show you as an example is a 2D automaton. And the automaton is going to do this function. I'll just talk about it for 1 minute. VGA screen. At t equals 0, at reset time, 1 pixel is going to be turned on, is going to be made white in the center of the VGA screen. And then a search pixel will be specified, and a random walk occurs. A random walk occurs through this space until the walking particle happens to hit the seed in the center, and it sticks and stops and never moves again. And then you randomly, from one corner or another, from one of the 4 corners, release another walker, which walks until it hits those 2 particles, and it sticks. And then you do it again. And as time goes on, you build up a structure called a diffusion limited aggregation. A diffusion limited aggregation. Google it up. It's a fractal. Why would it be fractal? Diffusion limited aggregation. So that's the one I will implement as sort of a full, ugly Verilog coding probably next time, Wednesday. This is all online. If you look on the VGA page, all of the code is there. You don't need to copy it in class, although it is useful for your brain to copy code. But if you want to print it out, it's on the VGA page. It's linked up from Lab 1. Look it up. Any questions? See you Wednesday.